In the first video, we explored some of the fascinating patterns and applications hidden within Pascal's triangle, and we developed the binomial theorem. We looked at how expanding a binomial corresponds to one single row of Pascal's triangle. In video 3, we'll explore how expanding a trinomial corresponds to two-dimensional space, and expanding a quadrinomial corresponds to a three-dimensional space. But how do we wrap our minds around the geometric representation of expanding a polynomial of 5 terms and beyond? Those are ideas and graphics we will explore in video 3. But before we get to video 3, let's take a look at what we learned in video 1 and use it to help us understand the multinomial theorem. Let's start by looking at a deck of cards and the 3 specific cards, the King, Queen, and Jack of Hearts. What if we wanted to look at how many ways these cards could be arranged in a row? In this example, if we were arranging the 3 cards, we would have 3 choices for the first card, and after selecting one for the first position, we would only have 2 choices left for the second card. And then finally, that only leaves 1 choice for the last position. Thus, it would be 3 factorial, or 3 times 2 times 1, which equals 6. We can see those 6 arrangements here, and we call each arrangement a permutation of the 3 cards. Remember, a permutation is just an ordered arrangement of a given set of objects. We could find the number 6 by the fundamental counting principle. That is, in a sequence of R procedures, if the first can occur in K1 ways, the second in K2 ways, the third in K3 ways, and so on, the total number of ways the sequence of procedures can occur is the product of all the individual ways. That is K1 times K2 times K3 all the way out to KR. In our example, 3 times 2 times 1 equals 6. Now suppose we want to know how many ways any 3 cards can be drawn one at a time from a deck of 52 cards, where, once again, order matters. Then we would have 52 times 51 times 50, which is 132,600 unique permutations of 3 cards. In this example, we are just choosing any 3 cards in a particular order. Thus, as we select the first card, we would have 52 to choose from. After we have selected one of the cards and now want to select the second card, we would have 51 to choose from, and then finally 50 choices for the third card. Once again, we have used the fundamental counting principle. Remember, in a permutation, the order in the arrangement matters. Think back to our 6 arrangements of the King, Queen, and Jack of Hearts. If the order does not matter, then there is just one combination of those 3 cards. That is, in a combination, all of the following are just the same group of cards. In a combination, order does not matter. Therefore, to obtain the number of combinations of the 3 cards out of a deck of 52 cards, we must divide the total number of permutations, which was 52 times 51 times 50, or 132,600, by 3 times 2 times 1, which equals 6. Since there are 6 ways to arrange the 3 cards chosen, and they are all the same combination. That is, in this case, we would have 22,100 combinations. Thus, 22,100 is the number of ways we could choose a group or a combination of 3 cards from a deck of 52 cards. For a combination, sometimes we simply say 52 choose 3. And here we can see the notation we use for 52 choose 3. We might even think of this as choosing 3 cards and leaving the other 49. In general, remember the notation for this is just the same notation we developed in video 1 for the binomial theorem. R choose K, which is R factorial divided by K factorial and also divided by R minus K factorial. It's the same symbol we use to denote an element in Pascal's triangle, called the binomial coefficient. Notice that 52 factorial divided by 49 factorial is just equal to 52 times 51 times 50. Thus, when we are doing 52 factorial divided by 3 factorial and also divided by 49 factorial, we were actually still just taking 52 times 51 times 50 divided by 6. Where did the 49 factorial come from and what is its meaning? Think of counting the number of ways we could distribute 52 cards to two distinct people in such a way that person A receives 3 cards and person B receives the remaining 49 cards. If we wrote 52, choose 3, and also choose 49, instead of 52, choose 3, it would make it explicit the number of cards each person is receiving. Since in the binomial theorem where we have R choose K, we have 52 choose 3, which is 52 factorial divided by 3 factorial and also divided by 49 factorial. We could also write that as 52 choose 49. Even though we could write 52 choose 3 and also choose 49 instead of just 52 choose 3, if we are dividing objects only into 2 groups, the accepted notation is just 52 choose 3. We would already know that 49 is in the other combination. The reason 52 choose 3 is equal to 52 choose 49 is both are really just calculating the same thing. Remember that both represent the number of ways we could distribute 52 objects to 2 distinct people in such a way that person A receives 3 cards and person B receives 49 cards. And in looking at the binomial formula, which again is given here, we could view K as the number of cards person A is receiving, and then we can view R minus K as representing the number of cards person B is receiving. Now let's take a look at another very common application and an example you may have seen before. What if we consider the number of different ways we could arrange the letters in the word Mississippi? If all the letters were unique, we could use the fundamental counting principle and it would simply be 11 factorial, since there are a total of 11 letters in the word Mississippi. However, there are 4 I's, 2 P's, and S is used 4 times. Looking at the word Mississippi, if we interchange the 2 P's, could we tell? The answer is no. To us, it would be the same arrangement. Thus, we have to adjust for the repeated letters that are actually just the same arrangement. We could adjust for the 2 different ways repeated by the 2 P's by dividing by 2 factorial. Of course, we would also need to adjust for the other repeated letters. For this problem, it would simply be 11 factorial divided by 4 factorial, also divided by 4 factorial, 2 factorial, and 1 factorial, which equals 34,650. Since 1 factorial actually equals 1, we don't really need to write that. This leads us to what's called the multinomial coefficient. Let's say we are expanding the polynomial d plus c plus b plus a, and we're taking that to the 10th power. What if we would like to know the coefficient of the term that includes d squared, c cubed, b, and a to the 4th, which notice is d times c times c times c times b, and then 4 factors of a. In other words, this is similar to the problem of dealing with the word Mississippi, because we can't distinguish between the 2 d's, the 3 c's, and the 4 a's. Thus, it would be 10 factorial divided by 2 factorial, 3 factorial, and also 4 factorial, which equals 12,600. The multinomial coefficient is just a generalization of the binomial coefficient. In general, the multinomial coefficient, as we see here, equals the number of distributions of R objects to M distinct recipients, such that recipient 1 receives K1 objects, recipient 2 receives K2 objects, and so forth. We do require that K1 plus K2 plus K3 all the way out to Km equals R, which ensures all the objects were dispersed. And of course, K1, K2, all the way out to Km be non-negative. But of course, this would just be one coefficient in the expansion. And there would be 286 different terms in that expansion. How do we know this? Well, let's investigate how this is determined. If we want to expand the polynomial, such as d plus c plus b plus a, that quantity to the 10th power, every term would have some combination of the four variables of the form d to some power r4, c to some power r3, b to some power r2, and a to some power r1, where of course all of those exponents are non-negative integers, and they must add up to 10. Notice that being non-negative means that as long as r4 plus r3 plus r2 plus r1 equals 10, any of them could be 0. So how many solutions are there to the equation r4 plus r3 plus r2 plus r1 equals 10? To explore the possibilities, let's assume we want to know how many ways we could divide 10 identical balls and place them into 4 bins. In this case, we would be trying to solve the same equation. One popular way is a technique usually referred to as the stars and bars method. Using this method, we will represent the objects to be divided by stars. Thus, see here we have 10 stars. Then to indicate dividing the objects into groups, we will use bars as dividers. To divide these 10 stars into 4 groups, notice that we only need 3 dividers. Let's look at some possibilities. In this first example, this would represent the first bin getting 2 balls, the second getting 3, the third getting 1, and the fourth getting 4 balls. In this second example that you see here, this would represent the first bin getting 1 ball, the second getting 6, the third bin getting 1, and the fourth getting 2 balls. And in this final example, here we see an example where the first bin is getting 8 balls, the second is getting 2, and bin 3 and 4 is getting nothing at all. Therefore, the number of different ways we could divide 10 balls into 4 bins is the same as asking how many ways could we arrange 10 stars and 3 bars. Since we cannot distinguish the stars from one another and likewise the bars, this is similar once again to the problem of asking how many ways we could arrange the letters in Mississippi that we looked at earlier. Thus we have a total of 13 items, that being 10 stars and 3 bars, to arrange, and the total number of unique arrangements would be 13, choose 10, and choose 3, or 13, choose 3, or 13, choose 10. Again, remember we had 4 bins, but we only needed 3 bars for our dividers. Thus, the formula to determine the number of terms in the expansion that we originally started with, that we see here, is in the numerator we would have r plus the quantity m minus 1, all of that factorial, divided by r factorial and also m minus 1 factorial, where r was the number of stars and m was the number of recipients or groups we were dividing them into. Or r is the index of the polynomial and m represents how many terms are in the polynomial. Thus, for our initial question, which was asking how many terms are in the expansion d plus c plus b plus a all to the 10th power, we now have a formula which we see here. We can calculate the result, and that result would be 286. That's a lot of terms. If we wanted to fully expand the polynomial, we certainly wouldn't want to have to find each coefficient separately. Now, the multinomial theorem, depending on the variables we use, can be stated as we see here, where, of course, we still have the multinomial coefficient of r factorial, choose k1, k2, all the way out to km, just as we stated earlier. This may look rather intimidating, but in actual practice, it's quite easy to apply, and in fact, we've been using it already. The multinomial theorem does make it convenient to find a coefficient for any particular term in an expansion. For example, if we wanted to know the coefficient for the term including d cubed c b squared a in the expansion of d plus c plus b plus a to the 7th power, it would simply be 7 factorial divided by 3 factorial, 2 factorial, 1 factorial, and 1 factorial, or 420 d cubed c b squared a. If we were expanding the polynomial 2d plus c minus 3b plus a all to the 7th power and wanted to know the coefficient containing d cubed c b squared a, we could compute the coefficient the same way, and in this case we'd take the first term 2d to the 3rd power, the second term c to the 1st power, or we'd have the result 30,240 d cubed c b squared a. The multinomial theorem also has a variety of applications in statistics, as well as many other disciplines. Let's take a look at what is referred to as the binomial experiment. Remember earlier when we were discussing the number of ways we could distribute cards to two distinct people. In a binomial experiment, we have the number of trials in an experiment, and each trial can result in just two possible outcomes. Usually we let P represent the probability of success on an individual trial, and Q represent the probability of failure on an individual trial. For example, if P equals 70%, Q would equal 30%, since they must add up to 100% or 1. Therefore, Q always equals 1 minus P. We do require that each trial be independent. That is, the outcome of any one trial does not affect the outcome of the other trials. The formula for this type of problem, called the binomial probability distribution, looks like this, where X represents the number of successes. Notice that this is really just the binomial formula we used earlier. Let's look at an actual example. In a hospital, 30% of patients are dying because of a particular disease. So the probability that a patient is cured is 70%. If 12 patients are admitted into the hospital, what's the probability of exactly 8 of them surviving? In this case, the probability of success would be 0.7 or 70%. The probability of failure would be 30%. Thus we have 12 choose 8, and then we would take 70% to the 8th power and 30% to the 4th power. And here that would be approximately 23.11%. These types of problems also extend to the multinomial theorem, or in this case we say the multinomial distribution. Thus we can consider more than two outcomes. That is, suppose a multinomial experiment consists of n trials, and each trial can result in a number of k possible outcomes. We call those outcomes event 1, event 2, and so forth, or E1, E2, and so forth. Suppose further that each possible outcome can occur with the probabilities P1, P2, all the way out to Pk. Then the probability that event 1 occurs n1 times, event 2 occurs n2 times, and event Ek occurs nk times is n factorial over n1 factorial, n2 factorial, all the way out to nk factorial, times each probability raised to the appropriate power, where n1 plus n2 all the way out to nk must add up to n. In these types of applications, we do require the experiment has the following conditions. 1. The experiment must consist of n repeated trials. 2. Each trial has a discrete number of possible outcomes. In mathematics, we say a set of data is said to be discrete if the values belonging to the set are distinct and separate, or unconnected values. 3. Doing one trial does not affect the outcome of other trials. And 4. Any trial must have one of the considered outcomes. Let's look at an example using the multinomial distribution. What if we know that the blood type distribution in the United States is as follows. 44% have blood type O, 42% have blood type A, 10% have blood type B, and 4% have blood type AB. In these percentages, we're going to ignore the RH factor. That is, we're grouping A positive and A negative blood types into the same category. Now let's take a look at an example. If we have a random sample of 40 people come in and give blood, What's the probability that exactly 18 will have blood type O, 16 will have blood type A, 5 will have blood type B, and 1 will have blood type AB? Notice any person's blood type does not affect another person's blood type, so the trials are independent. Also, each person must have one of the 4 types given, and we have 40 trials. The probability of this particular outcome would be 40 factorial over 18 factorial, 16 factorial, 5 factorial, and 1 factorial, times each probability raised to the appropriate power, which is approximately equal to 0.727277%. Looking at what we have done, the 44% or 0.44 represents the probability of any one person having blood type O, and raising it to the power of 18 gives us the probability of that occurring 18 times, and so on for the rest of the probabilities. The expression 40 factorial over 18 factorial, 16 factorial, and 5 factorial gives us the total number of ways we could have this combination of people with those outcomes. As we can see, the multinomial theorem can be quite easy to use and does have applications across various disciplines. However, within those applications, we are usually finding one specific term in the expansion of a much larger expression. For example, earlier we looked at the expansion of d plus c plus b plus a to the 7th power and wanted to find the term that included d cubed c b squared a, and we found it to be 420 d cubed c b squared a. However, we're also now able to determine that there would be 120 unique terms in that expansion. Using what we have discussed so far, it would be a bit tedious to find them all. Also, when we were developing the binomial theorem, we had an interesting geometric interpretation. We had Pascal's triangle and all of its interesting qualities. Do we have anything like that we can relate expanding polynomials which are larger than 2 terms? It just so happens that we do. In video 3, we're going to investigate some unique and fascinating qualities of these relationships and develop the formula that will help us find all of the terms in the expansion of a polynomial. So now the real fun begins, where possibly you will be exposed to ideas and graphics you have never seen before.